Thank you all for standing by, and welcome to our webinar entitled Climate Change, Uncertainty, and Communication. These webinars are an initiative of the Ohio State University Climate Change Outreach Team, a multi-departmental effort within the university led by OSU Extension, Ohio Sea Grant, Bird Polar Research Center, and several other OSU departments to help localize the climate change issue for Ohioans and Great Lakes residents. I am Jill Gentis-Benicki from Ohio Sea Grant and Stone Laboratory, and joining me today is Mark Berliner. Dr. Mark Berliner is professor and chair of the Department of Statistics at Ohio State University. He has served as the Geophysical Statistics Project Leader at the National Center for Atmospheric Research, as a contributing author to the Intergovernmental Panel on Climate Change, and as co-chair of the American Statistical Association's Advisory Committee on Climate Change Policy. We're delighted to have Dr. Berliner here today to discuss climate change and addressing uncertainty. Before we do that, a few logistical issues as we get started. During our presentation, all participants will be in a listen-only mode. Afterwards, around 1:15, I will conduct a question and answer session. If you would like to ask a question during the presentation, please feel free to use the chat feature located on the right-hand side of your screen, and I will collect and pose the questions out to Dr. Berliner at the end of his presentation. We have nearly 200 participants so far on this webinar, a great diverse group representing governmental agencies, academia, and nonprofit groups from the Great Lakes and around the country. Please keep those questions coming throughout the presentation. We should have a great Q&A session. As a reminder, this webinar is being recorded and will be posted onto our website for later viewing. Also, we will post a webinar survey in the chat feature toward the end of the hour. Please take a few minutes after the webinar to fill out that survey. It will help us continue to bring you better webinars. So without any further delay, I'd like to introduce Dr. Mark Berliner from Ohio State University, who will present Climate Change, Uncertainty, and Communication. Dr. Berliner, I'm going to unmute you. So you should have a voice now.
Do I have a voice?
And I am going to also give you the ball here. 1 second. All right, you should be good to go.
Okay, thank you. Thanks, Jill, for handling all of this setup, and Christina as well. And thank you all for joining me for about 45 minutes here. This is a kind of a short time, so I have a lot of discussion points. This is primarily going to be a discussion and some issues. I don't think I have any great solutions to all of these problems. I hope you're not disappointed in that. I can't believe you would expect the killing answers to everything here. But I think there's some interesting issues that I'd like to bring up and discuss with you. So I'll begin with a few notes and then present a couple of examples. Some of the more interesting and sometimes even controversial things I'll mention in the closing discussion, and I hope you find some of this interesting. So what are the fundamental challenges? At least, obviously, the most fundamental challenge is that the climate system is incredibly complicated, highly diverse, and there's a lot to it. But I'm assuming that and going on and emphasizing mostly things that have to do with probability and statistics. So one of the critical things, of course, we begin with the notion of uncertainty quantification. The climate problem is replete with all sorts of issues. And there are natural approaches for doing that. That's how I got into this business and how many of us got into this business. And that is that as statisticians, we have lots of techniques and approaches available and hope to apply them. In addition to just quantifying uncertainty, however, that's hardly enough. We also need to manage that uncertainty, ask ourselves how that uncertainty propagates into our policies and solutions. What are we going to do about it? And again, there's a framework at least that exists for doing that, Bayesian decision analysis. And although I won't actually do any serious Bayesian decision analysis today, I just want to allude to the fact that there is this framework available. What I want to talk about mostly today, however, is communication. It's a challenge to all of us and fundamental to the climate change issue as we scientists try and communicate and deal with the problem. First and foremost, it's sort of obvious, but please bear in mind that how you communicate and what you communicate obviously depends on your audience. I certainly give a very different talk if I'm talking about climate change to scientists as opposed to the sorts of things I might say to the public or to decision makers. Even within that group, there's subgroups of people who get different sorts of information or who have different backgrounds, and then obviously there's different ways of communicating what we have to say. How about communicating probability? This is often noted as a real challenge that people don't understand probability, but I actually don't believe that. I think people do understand probability. They have an innate notion about probability, and certainly when I give a couple probabilities of different orders of magnitude, people certainly can appreciate them. I think there are other issues to that, however, that are a little bit more critical. I think there's a natural response among the general population that when we start talking about probabilities, they think we're doing it because we're just kind of uninformed. And we're resorting to the notion of just starting to make stuff up. Make stuff up. Make stuff up. Excuse me. There's also something even more critical in that. I think is just some facets of human nature that are in contradiction to the notions of probability. I contend to you that virtually everybody just kind of hates uncertainty, except for statisticians, of course. That's why we make a living. Let me tell you a little anecdote and allude to that kind of indicates what I mean. There's this fellow, a young guy named Nate Silver, who's doing lots of interesting stuff, has become very, very high profile for doing some statistical analyses regarding polls, and in fact he became quite famous by doing some analysis combining polls during the last presidential election in the U.S. I saw him interviewed on the American television show 60 Minutes, and at one point he had mentioned how he had assigned probability of 0.7 to the event that Obama would win the election. Again, 0.7. And so the correspondent, obviously a very intelligent, well-educated, and smart person, responded by saying, "Oh, so you're convinced that Obama's going to win?" And you could see Silver's expression, and I'm trying to make the same expression now, though you can't see me, and that is, "Oh my gosh, no. I'm saying the probability is 0.7, and then he tried to explain what that means in terms of gambling and something else. But my contention is that everybody knew what 0.7 meant as opposed to 0.3 or 0.8 or something else. It's not the notion that that one doesn't understand probability. It's the notion that one tries to instinctively process even probabilistic information and make it something certain. And I think that's something that we have to deal with. And it's an issue that I think will continue to be in our way a little bit. One thing I'd like to urge that we all make clear is that probability is not just something where we make something up and guess. Probability has a mathematical theory. It is a mathematical theory. It's as theoretical and well-founded as any other kind of mathematical approach to issues that are relevant. I think it's also, many people say the statement in many different ways, weather is what you get, climate is what you expect, all those sorts of things. But I really like to think and argue to people that climate is equal to the parameters of the probability distribution of weather. So with climate change, then, that changes the distribution of weather. It doesn't change weather, so to speak, but just rather the distribution of weather. Now, people have said that in many different ways. Some people make up little examples. What's one of the most famous that's circulating, that climate change is making the dice biased in other directions in terms of extreme weather events, for example. I think Jim Hansen and others have made that sort of setup. I think that's right, but I think if we keep separating the notion of weather and climate, we can make some progress in that direction. The other reason I like this statement that the probability distribution of weather is affected by climate is that people are always constantly hearing things about probabilities in weather. People know about the probability of rain. They hear it every day. Probability of various other events is something that I think that even the general public is really quite comfortable with, and I think we should make use of that comfort when we can. Next, the other aspect about communication of the decision aspects of any climate change or any other context in which we have uncertainty is the notion of risk. The notion of risk is, of course, if you have technical background in the area, you know that's the basis for choosing actions. It's a mathematical notion that allows us to formulate and derive actions in some kind of optimal or close to optimal sense. Before I go further into this, you'll notice that I'm doing something with two columns often. This is actually part of the communication trick that I think is useful. That is, I have a non-technical column and a technical column, and I'm actually suggesting that I would not necessarily use one or the other, but I often like to use both. I think even non-technical people like to see that there's some mathematics, so even though if I don't go through the technical stuff, they like to see it. Also, if depending on who you're talking to, if you're talking to a committee of people at a business, for example, there will be the managers who make the decisions, but they will have technical support staff. And it's really nice to have both of these up so that the technical support staff can then maybe supplement the information to the decision makers so that they can see what's going on. Okay, so back to the technicalities. What is risk? From our point of view, we define risk as expected loss, which sounds like I'm doing a circle, but the idea is very simple. It's a mathematical way of accounting for both the possible losses and their probabilities. That is, we don't just separate potential losses or costs associated with events, but we also have to know something about their probabilities to begin the decision process. So, for example, we can bring in the notion of high impact yet low probability events and indicate how they become important. They become important through the calculation of risk. The formula's on the right-hand side. I'm not even going to say what it is, but the notion is that low probability events can be very important. And I think some people don't quite recognize how that can happen. So if you can read very carefully there, you see a little tipping point anecdote. No, it's a note to myself to tell you a story. As was mentioned, I visited the U.S. Congress a few times and talked to people and tried to communicate issues about climate change. And at one point I was talking to someone who asked me about tipping points and said, essentially, the quote is that they asked me, I don't really believe in these terrible tipping points, that there's going to be a disaster in 10 years or something like that. And I said, well, my response was, first of all, tipping points vary in their level of severity, but more importantly, I said, okay, I'm not going to tell you that a tipping point is going to happen. What if I don't tell you that it's definitely going to happen with a high probability? What if the probability is only 1% or 5%? And the person I was talking to froze because although they had never thought about it in these terms, they instantly saw the point that they have to make the decision not necessarily just because of high probability issues, but also because of the potential impacts. So the more we emphasize that, I think the better off we can be. The other thing I like to do is that even though it's incredibly artificial, I made up these numbers just for illustration, sometimes these artificial illustrations are actually useful. So what you're looking at is a simple little illustration that I made up just to demonstrate how it is possible for this risk function or this risk notion to be responsive to high-impact, low-probability events. So this example I would describe as, think about the marginal cost of Sandy-like storms due to climate change. And let's pretend that that's about $50 billion. I've just made up a number. I have to, whenever I use an example like this, make sure that people understand that I'm doing this as an illustration. The actual cost of Sandy was is in the range of something like 120 or 140 billion dollars. But let's pretend that it makes sense to think about the extra severity associated with Sandy is about $50 billion due to climate change. Let's pretend that I can actually think about some sort of strategy of mitigation or adaptation that would cost me $5 billion. Is it worth risking that $5 billion to protect against extra marginal notions like Sandy? Well, it depends on the probability of a Sandy-like event. And I'm willing to call that probability small. But if I do the optimization reflected in the table on the right-hand side, you get to a conclusion that you can explain to somebody. The mitigation would be something that I would recommend if the probability of Sandy-like events was at least 10%. So again, you see the small probability, more realistic numbers, I could get even more things. But the point is, I can get to a semi-realistic statement that involves small numbers, small probabilities. And I don't even have to tell you what that probability is. I just have to give you a range and I get some kind of information and transfer at this point. If I was actually talking to a decision maker, I would also remind that decision maker that this is actually an unfair estimate because, of course, the mitigation might apply to several Sandy-like events, not just one. So, in fact, we can hopefully get even more money for our investment. What are some of the other issues? Some of the other issues, and at least maybe it's my personal bias having talked to people in the U.S. Congress, is that there's some extremely compelling and difficult issues that are because of economics and politics. There's no denying this, and I think we just have to adjust to it. The economic issues are not simply the natural economic problems of figuring out economic models or economic behavior, but the fact that we're talking to competing sectors. Obviously, I can talk about one economic issue about climate change to some people, and then have a completely different conversation about the same issue to people in West Virginia or Southern Ohio who represent districts full of coal miners. The politics of the situation is even more extreme because not only do you have to deal with sectors, you have to deal with regions, and you have to deal with the politicians' own issues and their own personal involvement. We often criticize politicians for acting only to do things to be reelected. So be it. Some thoughts to deal with this. The most critical thing I can suggest to people is that we need creativity in developing suggested actions. I'll say something that's potentially controversial to some, but at least I thought all along that the notion of trying to get cap and trade passed by the U.S. Congress was doomed from the beginning. So was that actually a poor investment of our time, and should we have been trying to think about other actions that had a better chance of making it through? The question that we could discuss at a bar sometime. The other issue that I think is really important is when we talk about the potential impacts, we don't need to focus just on the disasters because they're high impact but yet low probability, perhaps. I think that the accepted impacts are serious enough to motivate action. And I think that we would maybe make a lot more headway by making statements about the things that we are very confident in happening and use them to motivate action. The other thing is that we should take what we can get. That's a little bit extreme, but being upset when people won't do things like cap and trade, that's a problem, but that doesn't mean that even small steps aren't useful. For example, today, I think that the tide has turned among many people that mitigation is not so much what people are after, but rather adaptation. Now, you may think that some of the money that's spent on adaptation might be a waste or it's giving up, but I wouldn't tell Congress that I think, well, adaptation is silly. You should only worry about mitigation. We'll probably get nowhere by doing something like that. Okay. I wanted to show you very quickly a decision support toy example. And again, it's the kind of example that I wouldn't show to scientists. Well, I mean, I'm using it as an example for those of you who are scientists about communication. It's not the sort of thing that I consider very serious, but it's the sort of thing that you can use to make suggestions about the behavior of decision making that can be useful to potential decision makers. So this is very artificial, but let's just take a quick look. I imagine a situation in which I've refined everything so that there's only two future states of the climate system. Either we will really see climate change with all of its negative impacts, or in fact there really is no anthropogenic climate change. The climate is doing whatever it likes, and we're not causing it to do anything. Let's envision then a two-stage policy in which I will, over a period of time, agree that I can spend up to M dollars. M is just some maximum large amount of money that I'm willing to spend. And my decision making is done in two steps. Today I will allocate some proportion of M, okay, say B, so B is supposed to be a fraction. I'm going to choose how much of M I'm going to allocate today, and then allocate the rest of it later if necessary, and that's the trick. If I can allocate some amount of my money today and I do the job, I actually manage to mitigate most of the issues of climate change, then I don't have to spend the rest of my money. This two-stage notion is actually something that is very obvious to us all. The entire process of climate change and decision-making about it is a sequential process. But sequential decision theory is actually typically very difficult to explain. Again, you see the non-technical versus technical. So, again, with this very artificial example, I'm imagining that we will either mitigate climate change impacts or be fine if there is really no climate change. If there's really no climate change and I spend some money doing it, that money is lost, and we can consider that a loss. Finally, I'm going to make up a probability that climate change is a real issue. Let's just leave it as a variable for now. I'm not going to figure out what it is. I don't have to communicate the notion of the decision-making process by first finding that number. I can do the calculation as a function of that number and actually display some interesting intuition. The right-hand side then is an artificial but made-up loss function that'll do the job and sort of indicate what's going on. The losses due to the policy are in two steps. If there's really climate change, I'm going to lose the amount of money B that I have spent now, and then I'm going to lose the rest of my money later. Okay? If there's no climate change, then I'll know it after this first period, and I will have only lost the money that I've now spent. Then I can do a calculation for the risk and do some mathematics, and I find out that I have an optimal policy, an optimal fraction that I should spend as a function of the probability of climate change. Fine. What does it mean? First and foremost, and you'd be surprised how often one has to make this statement, the fact that I'm uncertain about the future of climate change and its impacts does not justify no action. That is, the optimal thing to do here is not zero. The optimal thing is not zero. That is, even though I'm uncertain, it can be the case that I should still take some sort of an action. Now, that's not very surprising to scientists, but I think some of us underestimate how much many people find it instinctive to say, well, I don't know, so I'm not going to do a thing. At the other end of the spectrum, however, is please note that the optimal action is also not extreme, okay? Even if the probability of climate change is very large, the optimal thing to do now is to only spend half my money, not all of it. So there's no reason to always try and overshoot with optimal, and instead find something that's reasonably plausible. What are some other things that I can learn from this example? First of all, I recommend that we study And again, this depends on the audience. Again, I don't think I can show these pictures to the general public, but I can certainly show them to business and the technical staff at a business to explain what's going on. The first thing I recommend is, again, remember that we don't have to specify all these probabilities in advance. We can study the risk, we can study the optimal policy as functions of the probabilities, and then look at them and find reasonable, plausible ranges of the probabilities later. The other thing to notice from this picture, and when you think about risk, is it's a constant reminder that although the optimal thing I might have, or for my probability, it's still not necessarily the case that your optimal thing is awful, okay? So just because your probability is a bit smaller than mine doesn't mean I have to convince you about that all the time. Our probabilities or our optimal actions might actually be very close, even though our probabilities might not be as close as one thinks. So that's what I've tried to show in this picture. Notice that it's nonlinear, and so the range on the plausible probabilities is actually wider than the range on the acceptable actions. And I think that's something that is underestimated in its value. Okay, I'm looking at my own clock to make sure I get to the fun stuff at the end. One thing I wanted to talk about a little bit too, and that is the quality of our information and the quality of how our information and how we communicate that to people. I have some personal perspectives on the use of climate models and the uncertainty that we associate with climate models, and I think they're maybe a little bit more aggressive than a lot of people have. First and foremost, and I will tell this to anybody, including Congress people, that the simple use of climate models as surrogates for the Earth and climate change studies is problematic. Okay, the climate model and the little computer model that I make up, little or gigantic, is not as though I have another planet that I'm trying an experiment on. There's always an offset that I have to deal with. And I think we just are better off by admitting that than hiding over it. I think there's also some resolution issues that are yet to be resolved. At least some of us doubt that today's climate models can make reliable projections at incredibly small scales, small spatial scales. And that's problematic for some decision support. Again, I'm not saying that there's no information in the climate models, but I don't think there's as much information necessarily about very small spatial scales as we might believe. One way to think about that is perhaps the uncertainty that I would associate with climate model output at small scales is so wide that it won't resolve or reduce the number of actions or optimal decisions in my mind. And finally, defend all of this. I think that some simple statistical analyses of ensembles definitely leave some uncertainty untreated. Ensemble variances, people tend to look at ensemble means and ensemble variances. Those do not account in any way for the biases or the model errors that are innate in climate models. One way to think about it is the following. Although we, of course, have limited numbers, ensemble sizes, just ask yourself this. If I had an infinite ensemble, okay, that is, in an infinite ensemble, the variance would get very, very small, but the infinite ensemble does not tell me what the true climate is going to be. It better not, because different models would give me different results. The infinite ensemble would tell me what the model's mean is going to be. And so if I do a procedure that doesn't account for or isn't sensitive, that sort of issue, I worry about underestimation or under-representation of uncertainty. Now, it is possible to do something about that, and here's the Bayesian approach. My time is getting shorter, so I'm not going to run through all of this. But it is possible to write down a model that explicitly accounts for model error, explicitly accounts for bias in the models, and yet still can make some conclusions. You have to pay the extra modeling strategy that's associated with the Bayesian approach, both computational overhead as well as as modeling overhead, but I think it's worth it in the long run to get a handle on those objects. If you don't do this, then the two terms that are underlined on the right-hand side here are ignored, and I think that's problematic. You can do it computationally, and you can still produce some results. And so these are summaries of Bayesian posterior distributions from models that have from analyses that have actually adjusted from model output. I'm not going to give you the details of this. Most of you recognize a picture that looks like this from IPCC. We get something relatively similar. But instead of going through those details, what I wanted to do was turn to some closing discussion. Again, it's a personal note and it's a suggestion, but I think we can kind of make a mistake if we don't couch our suggestions and our results in probability language. And so here's two columns of some examples. If you're talking to the general public and you tell people cigarette smoking causes cancer, a natural response that you'll get from a few people is that they'll say, no, it doesn't. My grandfather is 95 years old, has smoked 3 packs of cigarettes a day for 70 years and is cancer-free. How can you tell me that cigarette smoking causes cancer? Can you tell me that a ban on or control on assault weapons would lead to no school massacres? Of course not. Can you tell me that anthropogenic climate change caused or created the specific extra impacts that we associate with Hurricane Sandy? No. Those sorts of statements are perhaps a little bit too extreme. We tend to make them because we think we're trying to communicate to an audience who won't understand our probability statements. But on the other hand, I think it also opens the door to people saying, no, you're wrong. I would rather try and couch those exact statements in probability language. First of all, they're far more defensible. They get over this objection of a few counter cases, and they help actually make our case a little bit better. On the other hand, there's a price to be paid for that, however. It's not enough to make a ranking of these probabilities like the ones I've written here. To actually get actionable information for decision making, we need to explicitly quantify those probabilities, to know how far apart those probabilities are. So we have some extra work to do. Employ some more statisticians and probabilists. Issue number 2 that I wanted to make sure I got to, and that's this one. As scientists trying to communicate the issues of climate change, we also have to recognize that we're citizens. And so the citizen scientist actually faces some dilemmas. Typically, when we think about communication from a scientific point of view, we are to objectively, I left it in quotes because various people have various meanings about what objective means. But we're used to demanding amongst each other that we objectively present the best science available to us. But that we have to recognize that all of us are balancing that against our own personal concerns about the future. Okay? I certainly believe that climate change, if left alone, will lead to problems. How do I balance that and still talk about the objective aspects of the science that I do know? Well, first of all, what is objective? I'll let you fill in your own definition, but I'll tell you one more anecdote. As I was talking to congressional aides and visiting a lot of them, this is a rather, I hope they wouldn't be insulted by this, but it's a fact. Congressional aides tend to think of an objective scientist as one who agrees with them. I'm sorry, it's true. So when I was talking to Republican congressional aides, they were constantly complaining about some of the usual climate science people who were testifying about the severity and the potential severity of climate change. They didn't think they were objective. To be objective, you have to agree with the congressional aides. That's a problem. It's a fact. The other thing we have to constantly do as citizen scientists is always, of course, present our beliefs, but be open about the uncertainties that we have. There's a little hypothetical event that I can imagine happening in Congress, and And just imagining congressional people just going berserk when they saw something. So on day one, at a committee in the U.S. Congress, there's a bunch of testimony about how severe the case for climate change is and the impacts are there, and scientists justifiably saying things about how bad impacts will be, or even going as far as saying, act now or we'll see disasters into the future. The very next day, though, the same people are before a different congressional committee requesting more research dollars because our knowledge is so incomplete that we need a lot more money, we need a lot more people working on this problem so we can get better data and better models. And if the same congressman is on both of those congressional committees, they might have a strange comment to make to us. So do I have a solution to this issue? No, I do not. We each face our own decision problem, not the decision problem about climate change, but the decision problem about how we proceed as individuals and as a community. How do we report? What do we suggest? We solve this decision problem subject to a side condition, however, that we preserve both our personal and our scientific honesty and integrity. But I think too few of us maybe face that in advance and put our own perspective on that before we talk about this. The last couple of minutes, and I'm almost on time here, is this is really to the science community out there. It is to emphasize that we do have the right sorts of tools, or we're developing the right sort of tools from a probability and a statistics point of view and a computational point of view to deal with the complexities and uncertainties associated with climate change. We all know about the gigantic complexities in terms of the sorts of events that can happen. Here's a little overhead that I took off of the NOAA website, and you can see a description of so many issues. Next, here's another graphic that I took off of the U.S. Environmental Protection Agency site. And again, you can see all of the discussion about potential impacts, potential adaptations, both by geographic region as also sector of the community. You can see agriculture, you can see the oceans, you can see human health, human forests, energy production. All of these things interact. International issues, of course, are relevant. And can we possibly wade through all of this in some sort of a organized and useful fashion? And my suggestion is yes. The challenges to managing uncertainty in very, very complicated settings. What I mean by that is managing uncertainty across regions and across sectors. I think we can do that. I think we have to do some hierarchical Bayes analysis using all sorts of network models, interactive analyses. But my only point here is that these things are out there, they're being developed, and I urge the community to be aware that these things can happen and we can do them. What I envision is something that looks like this sort of a picture, in which we have to deal with observations, we have to deal with models and science, we combine them all, we pass them through impacts and losses and gains, but our challenge is still to represent the results of that in usable information at a decision support context. And I think all of these can be done. I think it's unfortunate that maybe parts of our communities do little pieces of this without interacting with other parts. But I think there is a hope to doing this in a useful fashion. Okay, I think I will stop there and look at questions. I was trying to be somewhat controversial to spawn interest. I hope I didn't overstate anything or insult anyone. But I think some of these issues are just interesting to talk about, and I tried to say them somewhat aggressively because of the time. Thank you all. I hope there was something in here and that I didn't rob you of 35 minutes of your life.
Yeah, we've gotten some great questions. Let me actually get started with a few. One question that several people had was dealing with cap and trade, and specifically you had talked about that it was doomed from the very beginning. Could you kind of talk a little bit about why you would say this?
I say that because my reaction when I was talking to congressional people is none of them. Well, I'm sorry. That was obviously an incorrect statement. Doubters about climate change and how then that reflected onto their policy decisions simply said that they didn't believe the economics of the model. And economics is not my area, so I couldn't defend it very well. But from the outset, they didn't believe any of the economics that was associated with it. Even if they bought into the notion that climate change was an issue and anthropogenic emissions was an issue, none of them were satisfied with the cap and trade economic basis. So I guess the people I found those sorts of objections from the outset, and so I personally thought it was doomed from the beginning, and that's maybe a suggestion to people who know more about the economics of these problems, is that they really need to understand and focus even more on that part of the problem.
Okay. Now you talked about climate models being problematic, and you talked a little bit actually about trade and cap and trade models. Could you maybe talk about a little bit about if models need to be updated with observational data? Do they give planners enough time or enough of the look into the future to actually plan for effects instead of reacting to current models? And also, just as additional, if they are problematic, what are the alternatives?
Okay. Let me restate what I meant by problematic. What I meant by problematic is we all understand that there's errors in the models aren't right, the models may have somewhat approximate physics, we all understand that part of it. They also try to link across so many processes, and those linkages are not always very well understood. What I meant by it's problematic, what's problematic is pretending or doing analyses as if those errors are not present, or as if the climate models are better than we all know they really are. That's what's problematic. There is no alternative in the sense that, of course, they provide us valuable information. So I'm not saying that we replace the models with something. What I'm talking about is how we analyze the output of the models. Okay? We have to develop methods which deliberately incorporate opportunities for us to analyze the model error, analyze the bias in the models, and try and make our analyses adjust for those. Now, sometimes that will give us wider uncertainty ranges associated with model output, but those uncertainty ranges are actually more indicative of what's going on. First of all, I just genuinely believe this, but second of all, as people test models and they fail, okay, there was recently an article in Science about how the regional models, some of the regional models associated with the U.S. NARCAP project failed their first attempt, failed their first check. When these models fail, sometimes they fail because we haven't provided enough of a wide range of uncertainty. And I think that then does us more harm than good. I'm not sure I really addressed the question. The question about timing of processing data, I'm not sure I understand that really. Are you talking about making, whoever asked, are you talking about making like sequential decisions at a day-to-day basis so that I don't actually have time to correct models based on the data? I wasn't sure what that meant. Sorry. If you like, you can email me or repose the question. I'll try and answer you another time.
Okay. Yeah, let me see if I can get some clarification. We had several questions asking if you could talk a little. You talked about ensembles, and a few of us weren't sure what ensembles meant. Could you define and kind of explain that?
I apologize. Yes. So a climate model is an implementation of laws of physics plus some data-based strategies about how we think the climate works. Those models sometimes have a variety of initial and boundary conditions that have to be set so that the model can be run. They also have various parameter settings inside them that have to be set to run the model. When I say an ensemble, what's typically done is people compute various possible specifications of those boundary conditions, more initial conditions in a weather context, and run the model several times based on different specifications of these various relevant inputs. The several runs of the model are what we typically call an ensemble, okay? It's an ensemble from the same model. Those runs are then often averaged to get an ensemble, or an overall ensemble average, or people use the variance of the ensemble to sort of indicate some notion of uncertainty. But again, with that variance computation, if it's done in a traditional sense, that's only looking at ensembling variability. It's not looking at these two. Does that help?
Yeah,
okay.
That really does.
Then there's a language, I don't know if I used it, but there's another language, multi-model ensemble. So I could also have a collection of different models, right? There's a model at Hadley Center, there's a model at NCAR, there's various models all over the planet. Different models, different climate models. They give different sorts of results. They have a lot of common stuff, but they also have some slight differences. So I can also talk about a multi-model ensemble in which I have individual ensembles from each of these models, and then my task is to combine them all across. Okay.
Okay. We had a couple of questions. I think it was with some of the slides later in your talk. One question was, can Dr. Berliner define what he considers small scale? What physical scale is relevant for climate? Are we talking town, county, state, something larger?
Oh, okay, very good. So even regional climate models tend to have spatial scales which are certainly much larger than the scale of a town. Okay, we cannot resolve climate or even regional climate at a scale that's relevant to making specific decisions about what's going to happen in a specific town. The spatial scales are simply too small as of now. So what happens when you do that? When you do a computation at a particular scale, you're acting as if the computation that you have available to you is true as an average across the entire region, whatever the grid box size is for your model. So it's by definition not going to be responsive to the variability of the difference between the temperature within the grid boxes or the precipitation patterns within the grid boxes. And therefore, if those things are relevant to the decision-making process, they're simply not reflected in the model. They can't be reflected in the model because the model can't be computed at that higher resolution. And so I think we just have to tell people that, there's a limit on the sorts of things that we can do at very, very small scales. Now, that's not to say that you can't use climate information to drive another sort of model that is at very small scales. But they're not the same as the models, the so-called large-scale climate models, nor even the regional climate models that have become popular. There's other sorts of models that I might make for a region like Columbus, Ohio, or wherever you happen to be. But the modeling and the strategy there is got to involve a lot of very specific climate and weather information from that location, as well as some information from the climate models. However, that's a very difficult task, and it's not well established about exactly how to do that, at least in my opinion. Does that help at all?
Yeah, definitely. Could you talk a little bit, expand a little bit more on what you mean by not focusing on disasters but the impacts? That was a question we had.
No, yeah, what I was trying to emphasize was that you don't have to motivate people to take action about climate change because you're worried about the sea level rise in New York City flooding the subways and people needing rowboats to get to their offices in Wall Street. I think that the impacts that we already can see happening and already have an influence are enough to motivate the need for adaptation and mitigation. Okay? We're already seeing that sea level rises, although it's not the disaster of a 20 sea level rise in the next 10 years. We don't have to go to that scale. The sea level rises that we're already seeing are enough to make storm surges much more severe than they used to be. They're enough to make other influences and that have real impacts and merit real attention now. And these things are much more well established, they have higher probabilities, and they can appeal more directly to individuals. That's what I meant. Okay, we don't have to just emphasize the worst case.
Okay. There were a couple questions dealing with, and I want to say it might have been slide 10, but it was the one dealing with the equation for calculating total cost. That I'm not.
Cost?
Yeah. Yeah, calculating total cost. Would that be right? I might be wrong in what slide it was.
But I'm on slide 8, and I see the notion that for this really artificial example that I made up, I said that if there's climate change, then I invest I lose B squared amount of money now, and then I have to spend the rest of my money later. If there's no climate change, I only lose the amount of money I spend now because I was making the completely artificial assertion that by the time I have to spend the next amount, I'll know whether or not I need it. That's why I stop here. Is that working?
Yeah. Could you also talk a little bit about slide 9?
Okay. So 9, what you're looking at here, let me go back to slide 8 for a second. I did the mathematics for this really, again, I can't overemphasize how artificial this is. It's just trying to make up an example where people could watch something but also see the impact of various kinds of assertions. So I had the mathematics for these definitions and then computed the actual risk. The actual risk, again, is the notion of loss times probability averaged, okay? And for this specific example, this thing turned out to be the risk. The risk is a function of the action that I take, and it's also a function of the probability of climate change. That specific function looks like this, okay? So I graph the risk function as a function of the action that I take, and then noted that I want to make the risk function small. For p equals the probability of climate change should be 1/4. Then the optimal action is right here. It's this 0.2. So this says that my probability for this crazy example, if I believe the probability of climate change impacts being a problem is 1/4, then I should spend 20% of my money now. Okay, and then see if that either takes care of the problem if there is no climate change, or I need to spend the remaining 80% later. Now, the whole point of this example is that even if the probability of climate change that I have in the back of my mind is huge, I still would never spend more than half my money now. I don't have to spend it all.
Okay, thank you. Thanks for the clarification. We have had quite a few questions dealing with more on your thoughts of climate models. One question that we had was, what is your personal feeling about the idea that given all the uncertainties of scientific climate change models, they might be as uncertain as climate or as human observations of communities close to nature like native people? Should any computation model value that? You wanted some hard.
Human memory and human history, much like, has its own biases and its own error over time. The sorts of errors and problems with climate models, I think we have a better understanding of their source. We know that the errors are coming from the fact that I had to make this sort of parameterization, or I had to make this sort of simplification. Given that, then I can hopefully go inside and start to diagnose that and compare it against data to help me understand the model error and the bias. So I do think there's a different value to the models that we use as opposed to purely human records, although I agree that there's information and other things there. It's just harder for me to imagine modeling the error in human records as opposed to trying to model the error in a physical model. Was that the question?
I believe so.
Okay.
Another question dealing...
Information in everything. The challenge is not to decide, oh, throw this out, throw that out. The challenge to all of us is to figure out the best ways that we can to extract the information that's relevant to us in our decision-making process.
Well, and you may have answered a little bit of this next question that I have. Do you see scientists and planners are able to deal with uncertainty sufficiently with existing decision support frameworks, or do we need to rethink and redesign decision support frameworks, for example, like adaptive management?
I think there's lots of specific approaches. Wait, let me clarify something. If you're talking about specific models for decision support, they're just computing a mathematical operation just like any other model is computing. So whether or not they're right or wrong is not the issue. Whether or not they need to be changed or not changed. I think what's probably missing from a lot of them, however, is how they present the innate uncertainty that comes from the climate models, for example. So I can believe that climate models are used as input to decision analysis tools. Economic models are input to those very same tools, and they do computations based on the inputs. I fear that those computations are not sensitive enough to the very uncertainties that I was talking about because not enough of work has been done on those uncertainties. It's propagation of uncertainty issue that I think I'm having a problem with. So it's not the model that needs, the decision support tool that needs to be changed. It's how we dig the inputs into that model and how we reflect the uncertainty in the output. I don't know.
Okay. Well, I have possibly two more questions before we end. One question is, when talking to the general public, such as like an educational program about climate change at a national park, what do you think is the basic and compelling way to describe uncertainty?
It's a $1 million question. I'm not sure. It's a partial joke. Personally, I'm not comfortable that other ways of having uncertain phenomena. So, like I said, some people like to represent the uncertainty issue as by saying, well, climate change is sort of like biasing the dice in something, or biasing some other friendly or well-understood gambling game. I'm not sure that that's useful. To me, being as clever as I can about showing different results and how they affect our uncertainty is the most critical thing. In terms of communicating it to the general public, in the example that someone just asked about, I'm not going to pretend I know. I don't have a silver bullet for you. I just won't make one up. Sorry.
Okay.
It's a great question, but
I know, isn't that a good question?
Yeah. I'd like to ponder it some more, but I'm not going to pretend I know the answer.
Okay. Well, the last, and this might be the million-dollar question too, is, in your opinion, what do you think the biggest stumbling block is when we're talking about trying to resolve climate change when it comes to policy?
I think it's right here. I think it's the economics and the politics of the situation. I think it's the fact that we're talking to competing sectors sometimes, and we have politicians in the middle. Frankly, I think local governments and local institutions are far further along in the game because they don't have this competing sector issue. But when I'm talking about the impact of climate change being bad for coastal regions, but then remediation or mitigation of climate change being bad for coal miners, to me, that's a stumbling block, and I think it's a problem for economics and for politics at large scales. At the scale of even a city or a smaller community, I think the disparity among the sectors is smaller, and therefore that's why I think we can see progress at local and even sometimes state levels. Right? California, for example, has something almost like a cap and trade, something like it, but California is not a primary coal producer either. So if you guys can manage this slide, I'd be grateful. Hello?
Oh, sorry. I was just about ready. I was just about ready to hand the baton back to me. Well, actually, we are out of time. We have some great questions that I will send over to Dr. Berliner, and if he has a few minutes of time to be able to answer those questions, we'll post those questions and answers up onto our site in the next couple weeks.
You can have me back if you want more about models and ensembles, too.
All right. See, they're a part two. Well, I wanted to, again, thank Dr. Berliner for his willingness to talk to us today about uncertainty and climate change. It was really an excellent discussion. Also, I want to thank NOAA, the National Secret College Program, and Ohio State University for funding this webinar. I did want to remind you that our survey URL for this webinar is in the chat feature, so please take a few minutes to fill that out. We would like to get your input as we develop a regional climate site, so please take the time if you could. I also wanted to refer you to resources and an archive of all the previous webinar presentations, which are located on our changingclimate.osu.edu website. This webinar is sponsored by the OSU Climate Change Outreach Team and will continue next month. We'll send out that information later this week. Thank you again to Dr. Berliner and all the participants on this webinar. We hope that this was beneficial and hope you'll join us again in an upcoming webinar. Thank you, Dr. Berliner, and have a great afternoon, everyone.